Welcome everyone. For today's prep, we're going to look at, or start to look at, polar regions. And so ultimately we're going to see how to graph just a few basic polar curves. We're going to get into more complicated polar curves in the next section. But for right now, we're just going to look at two basic curves. And then we'll start to explore these polar regions. All right, so let's start with our two most basic types of polar curves. So we have, in the first case, we have r equal to a constant. And let me switch colors there. R equal to a constant. And then in the second example, we have theta equal to a constant. All right, so let's think about what's going on with this first equation. What does this say? Well, we're looking at all the points. If we remember what r represents, this represents the distance from the origin. So we're looking at all the points that are 2 units away from the origin. Well, another way to essentially describe that is this is the circle of radius 2, centered at the origin. All right, so let's draw the circle of radius 2. So when r is equal to a constant, we have a circle. All right, so on our polar grid here, let's count out 2 units. So here's the origin, and then we just count out 2 units. There we go. And we find the circle of radius 2, and let's just draw that in. All right, pretty good. There we go. We've got our circle of radius 2. All right, so, well, now maybe a little trickier is the next one. What does it look like when we have theta equal to a constant? Well, when theta is equal to pi over 6, we want to start by finding the pi over 6 ray. So again, when we have, and let me just move real quick. When we have theta equal to a constant, this is going to be, well, ultimately it's going to be a line. But we want to start by looking at the ray for pi over 6. So the directed line segment going away from the origin with this specific angle. So essentially what we're doing is we're looking at all the points that have pi over 6 as a potential angle measurement. So if we look at our grid, if we look at our polar grid here, when we have pi over 6, remember pi represents the half of a circle. So that's half of the radians in a circle. And what we're doing is we're dividing the top half of our circle up into 6 pieces. So if we look at our polar grid, we've got one wedge here. So there's our first wedge. There's our second wedge, third wedge, and then fourth, fifth, and 6th. So that means this is the wedge for pi over 6. So that means, if we're keeping track, this ray is our pi over 6 ray. So essentially all the points on this ray have an angle measurement of pi over 6, or at least one representation with an angle measurement of pi over 6. We know that if we go around once and then add a little bit more, well, that's going to have a different theta value, but we could find a different representation that has an angle measurement of pi over 6. All right, so all of these points are going to fall on this curve. Well, we could also do the origin. So on this section, and let me make it a little bigger maybe. So on this section of our curve, these would be all points that have positive R value. So you can kind of think of this as like the positive section. Well, we could also represent, we also have the origin if we make R equal to 0. So R equal to 0 is perfectly valid. So that's going to fall on this collection of points. Well, if we make R negative, we get all the points over here. So we reflect them through the origin. So for R negative, we get all the points over here. So theta equal to pi over 6 gives us, has this positive portion of the line, has the point right at the origin, and then it also has this negative portion where the R values would be negative. So for this, the actual collection of all the points is everything. So it's going to be everything there. So when theta is equal to an angle, this is going, or a specific number, the actual curve is a line through the origin. Okay. So let's see how to deal with a polar region. Let's get our first little taste of a polar region now. So we have these two basic curves, R equal to a constant, theta equal to a constant. So let's go down to example 3. We're only going to do the first part of this one. So we're going to sketch the region, the section of the plane, where all the points satisfy both of these inequalities. So we're going to do just this first one. So we're going to do, we want our points to satisfy the inequality where R is between 0 and 2, and we want all the points that satisfy the second inequality as well. So the theta value is between 0 and 3 pi over 4. So we want all the points in the plane that satisfy both of these. All right, so there's a few different ways to think about this, but let's start with our R inequality. So when R is equal to 0, that's the point right at the origin. So we know the origin is going to be on this region. Well, let's look at the other side of this inequality, R equal to 2. So we know that is going to be a circle of radius 2. And if we're allowing R values in between 0 and 2, well, we're just going to fill in the circle. So let's draw our circle of radius 2 here. So we count out 2 units, and then we're going around the circle. And, well, not too bad. All right, so R equals 2 is just this outer edge. R equals 0 is going to be the origin, and then we want to shade in everything from there. So we're going to fill in, we're going to fill all this in. All right, so if it was just this inequality, R between 0 and 2, this is what it would look like. The circle, and then everything inside that circle. Well, we have another inequality, though. So we only want the points that have a polar representation where their theta value is between 0 and 3 pi over 4. So again, we want to start with the endpoints of this inequality. So theta equal to 0, what does that give us? Well, theta equal to 0 is going to be the positive x-axis. And, well, technically theta equal to 0 would give us the entire x-axis, because we would have the positive r portion, we'd have the r equals 0, and then we'd have the negative r portion. But for our case, we're only considering positive r values here. So this is going to be our theta equal to 0. Now, what about theta equal to 3 pi over 4? Well, let's figure out where is 3 pi over 4. And when we do this, we just want to remember pi over 4 splits up the first quadrant into two pieces. So pi over 4 is right here. So 2 pi over 4 would be the positive y-axis, and then 3 pi over 4 is going to split up the second quadrant. So 3 pi over 4 is going to look something like this. And if it was just this inequality and we were considering just positive r values, well, then it would be everything extending from this theta equals 0 ray and going all the way. So actually, it would be everything starting at this theta equals 0 ray. I had it. Let's see if it corrects. There we go. And extending, rotating all the way around to that 3 pi over 4. So it's going to be all of that. That whole big wedge. But we only want the section that's inside that circle too. So we kind of want the intersection of both of the regions. So first let me kind of just fill in a little bit here. Yeah. Tough coloring. Let's see. Let's try this. Okay, good enough. So if we want all the points that satisfy both of these, we're just looking for the intersection. So the intersection is this wedge. So that is our polar region. So all the points inside this region here simultaneously satisfy both inequalities. So the points out here only satisfy the theta one. The points over here only satisfy the r1. But together, it's these points that satisfy both. So there's our polar region. We're going to see how to do this with some other examples in class. So we'll see you then. Bye-bye.